Hello everyone, welcome to my research presentation. For this assignment, I wanted to find a topic that bridged the gap between port operation, which we are studying now, and the port governance, which is coming next. So to do this, I decided to look ahead to the lecture slide for topic 4. As I was reading through the material, I stopped at slide 28. And on this slide, under the section for green supply chain, there's a list of tools. Hidden in that list is a single simple bullet point: shore power supply. The lecture notes identify that this tool exists. However, they do not explain how it works. The notes don't tell us how a port actually connects a floating, moving vessels to a high voltage city grid. They don't mention the risk of electrocution, the massive frequency mismatch, or the multi-million-dollar infrastructure required. Then I realized that while the policy might be covered later, the engineering reality behind this concept, technically known as code ironing, is a significant gap in our understanding. Today, I will fill that gap. I will explain the engineering constraint, the operational risk, and the governance dilemmas of onshore power supply. So first, let's establish the context. When a ship docks at a port, it turns off its main propulsion engine. However, the ship does not sleep. A modern container ship is effectively a floating city. It requires a massive amount of electricity to run. It could run crew life support, such as lighting, kitchen, air conditioning, or it could run bridge system like the navigation and the communication. And the most importantly is the reefer containers to keeping food and the medicine frozen. So to generate this power, ships have traditionally run their auxiliary diesel engine 24 hours a day while parked at the berth. So the problem is these engines burn bunker fuel or marine diesel. According to 2020 study by Skane and Horrocks-Tile, the effective solution to develop a zero-emission port, burning these fuels at the dock release a high concentration of sulfur oxidized or SOx, nitrogen oxidized or NOx, and particulate matter PM 2.5. Because ports are often located in the heart of major city, these toxins are released directly into the lungs of local residents. And then cold ironing or onshore power supply is the engineering solution. It involves plugging the ship into the local city grid so it can turn off those diesel engines completely. A quick side note, why is this called cold ironing? It is a historical term from the era of coal-fired steamship. In those days, keeping a ship ready meant keeping the fire burning. When a ship docked and the engines were finally stopped, the fire was allowed to die down, and the iron engine literally went cold. Today, we use this 19th century term to describe 21st century technology. Now, we move to the core of my research. Why isn't every port doing this? It comes down to physics, specifically the frequency mismatch. And this is one of the most critical technical constraints. Like national grid in New Zealand as well as in Europe and most of Asia, the power grid vibrates at 50 Hz. And for international shipping, The majority of ocean-going vessels are built to international standards, where the onboard equipment run at 60 Hz. This incompatibility is strictly regulated by the IEC or IEEE 80,005 and 1 standard for utility connection. If you were to simply plug a 60 Hz ship into a 50 Hz port socket, the ship motors would run 17% slower, and the cooling fans would fail, the equipment would overheat, and the ship electronics would be destroyed. To solve this, the port cannot just install a plug. They must build a massive facility called a static frequency converter. This equipment performs a three-stage surgery on the electricity. 1. It's a rectification. It takes the raw AC power from a city and converts it into direct current, DC. Second, inversion. It takes that DC power and uses high-speed transistor to chop it back up into AC, but this time at the precise 60 Hz frequency required by the ship. And finally is the transformation phase. It steps the voltage up to 6,600 volts or 11,000 volts to push it across the cable. This equipment takes up valuable terminal space and costs millions of dollars per berth. The second hurdle is the physical connection. We're dealing with high voltage copper cables. They are far too heavy for a human to lift. Part must be installed a robotic cable management system. These are hydraulic cranes that lift the cable to the ship. Crucially, they must automatically adjust tension. As the tide goes out and the ship drops, the robot must feed out more cable. If it fails, the cable snaps. If it feeds too much, the cable hangs in the water. And to give you a sense of the operational reality, I want to walk you through the actual procedure of connecting a ship. It is not like plugging in a toaster. It is a 45 minutes operation involving high-risk protocols. The first step is alignment. The captain must park the ship within a 10 meters window of the cable pit. If they miss the mark, the cable simply won't reach and the operation is cancelled. Step 2 is the connection. Port workers engage high voltage safety protocols. They connect the massive plugs, but the power remains off. They use a specialized socket box with a physical interlock, which is physically cannot open if there is live current. Step 3 is synchronization. This is the most dangerous moment. The ship generator is running at 60 Hz. The shore power is running at 60 Hz. They must be perfectly synchronized in phase. If the switch is thrown when the waves are slightly out of sync, it can cause an arc flash or an explosion in the switchboard. Step 4 is the load transfer, also the final step. And in this step, they don't just switch over instantly, they perform a soft transfer. The shore power slowly ramps up its contribution while the ship slowly ramps down its engine. Only when the shore is carrying 100% of the load can the ship finally cut its diesel engine. And as you can see, this requires highly trained staff and strict safety governance. Beyond the engineering, there is a massive governance issue. the chicken and the egg dilemma. According to the US EPA's technology assessment, widespread adoption is stalled by a split incentive. For cold ironing to work, two parties must spend money simultaneously. First one is the port must invest approximately 5 to 10 million to build the station, and the ship owner must invest approximate 1 or 2 million to retrofit the ship with a receiving switchboard. And here is the stablemate. Shipping lines say, why should I spend millions fixing my ship if the ports don't have the plugs yet? And then the ports say, why should I build the plug if the ship can't use it? Furthermore, electricity is often more expensive than bunker fuel. So even if the plug exists, a captain might choose not to use it to save money. This is where port governance is essential. The port authority must create financial incentives, like offering a 20% discount on port dues to make electricity cheaper than diesel. For part 6 is a case study. Now, let's look at two ports that have solved this. The first case study is the case study of Port of Los Angeles. They utilized a governance strategy based on regulation, the STIC approach. Under their Clean Air Action Plan, they mandate that frequent visitors must plug in or face fine. Their reports show this had led to an 87% of reduction in diesel particulate matter. And the second case study is Port of Gothenburg. They focus on innovation. They are first to develop the green cable for oil tanker. By pressurizing the plug with inert gas, they ensure that spark cannot cause an explosion, proving that even hazardous ships can use this technology. So, to conclude, let's look back at slide 28 of our future lecture note. We start with a single bullet point, but we have unpacked that this single point represents. First is the engineering complexity, like the frequency converter. Second one is the operational danger, like the synchronization process. And finally is the governance challenge, such as the economic statement. And this shows that green ports are not just about policy, they are about mastering the technologies that make policy possible. And finally, let's look at a small video that I have made to conclude all my work. Here's the video.
Ever see a giant ship at port and wonder, why not just plug it in? Well, the answer is complicated.
Okay, so the solution seems obvious, right? Just plug them in. But it's actually a huge engineering headache.
Think of these ships as floating cities. And at port, they're running on the dirtiest fuel out there.
The green solution is called cold ironing. The idea is to plug in so the ship's engines go, well, cold.
Okay, simple idea, right? Except it runs headfirst into a huge physics problem. A shocking one, actually. Here's the problem. Most of the world's grids are 50 Hertz, but international ships, they run at 60. The fix? A multi-million-dollar station that does this crazy three-step dance to convert the power. And it's not just the physics. We're talking about cables so heavy, no human could possibly lift them. So, you need robotic cranes. They lift the cables, plug in the ship, and even adjust for the tide. So yeah, this is far from plug and play. We're talking about a super precise, high-stakes procedure.
They call it the high-voltage handshake. Every single step has to be perfect, done by highly trained crews. And that synchronization step, it's the most dangerous part. Get it wrong, and the whole switchboard can just explode.
So with all this tech and danger, you have to ask, who's footing the bill for all this? Get this, the port has to drop $10 million per station, and the ship owner, $2 million per ship. And that creates this classic standoff. Ports won't build plugs if ships can't use them. and vice versa. Okay, so with all these problems, how has anyone actually pulled this off? Well, a few ports have. Turns out there are two ways. LA used the stick approach, a law. Gothenburg just innovated their way out.
And the result in LA? A mind-blowing 87% drop in ship pollution. That is a massive deal.
So yeah, it's way more than just a plug. It's a huge challenge in engineering, economics, you name it.
It just goes to show, sometimes the simplest ideas are the ones that test our engineering limits the most.